After completing this presentation, you will be able to identify 4 widely used temperature scales, convert from one temperature scale to another, explain methods of heat transfer. What is heat? All matter can exist in 3 different states: solid, liquid, or gas. The different states are achieved by the level of electron excitation. Heat is apparent change in electromagnetic energy in any matter, resulting from the relative state of excitation of electrons. Simply put, the more the electrons of an element are excited, the faster the electrons move. The faster they move, and the closer they are together, caused by pressure, the more friction is created, resulting in heat. What is temperature? Temperature is the heat of an object measured by its intensity or degree on a defined scale. Absolute zero, the lowest temperature possible. There is no electron movement and energy is non-existent. This point is theoretical only and can never be reached. There is always energy present in the universe, therefore a zero energy state is not possible. Temperature. Temperature is a measurement and generally expressed using one of the following scales: Kelvin, Celsius, Fahrenheit, or Rankine. Relative scales. Temperature scales based on the freezing point and boiling point of water. Using the relative scales to express temperature, you can have a negative number. The relative scales are Celsius, Fahrenheit. Absolute scales. These are temperature scales based on absolute zero as the lowest value on the scale. Using the absolute scales to express temperature, you cannot have a negative number. The absolute scales are Kelvin, Rankine. Celsius temperature scale. The Celsius temperature scale is the SI, metric, version of the old centigrade 100 degree temperature scale. Notes about the Celsius scale. 0 degrees Celsius is the freezing point of pure water. Temperature divisions are the same as the Kelvin scale, where 100 degrees separates the freezing point and boiling point of pure water. Minus 40 degrees Celsius and minus 40 degrees Fahrenheit are the same. Therefore, minus 40 degrees is the convergence point of Celsius and Fahrenheit scales. Kelvin temperature scale. The Kelvin temperature scale is named after Lord Kelvin, who postulated that the lowest temperature possible would be the point at which all molecular motion ceases. Absolute zero is that theoretical point. Notes about the Kelvin scale. Zero is absolute zero. There are no negative values. Temperature divisions are the same as Celsius, where 100 degrees separates freezing points and boiling point of pure water. Kelvin versus Celsius. Shown here on the right are the 2 scales of Kelvin and Celsius. If you notice that there really is only an offset of 273.1 degrees. Just to say there that 0 degrees Kelvin is actually minus 273.1 degrees Celsius, and 0 degrees Celsius is plus 273.15 degrees Kelvin. To convert Celsius to Kelvin, Kelvin is equal to the degrees Celsius plus 273.15. To convert Kelvin to Celsius, Celsius is equal to Kelvin minus 273.15. Fahrenheit temperature scale. The Fahrenheit temperature scale is a non-SI scale and is named after its inventor. It was intended to help sea navigation. Notes about the Fahrenheit scale. 32 degrees Fahrenheit is the freezing point of pure water. Degree increments are smaller than that of Kelvin or Celsius, where 180 degrees separates freezing point and boiling point, 212 degrees Fahrenheit, of pure water. 0 degrees Fahrenheit is the freezing point of salt/water brine, basically seawater. Minus 40 degrees is a convergence point between Fahrenheit and Celsius. Rankine temperature scale. The Rankine temperature scale is a non-SI scale and starts at absolute zero. Notes about the Rankine scale: 491.67 degrees Rankine is the freezing point of pure water. A lot different than that of Fahrenheit. Fahrenheit is 32 degrees. Temperature divisions are the same as Fahrenheit, where 180 degrees separates the freezing point and boiling point of pure water. But similar to Kelvin, it starts at absolute zero and there are no negative values. Rankine versus Fahrenheit scale. Notice to the right there's a comparison here between the Rankine and the Fahrenheit scale. And note, on the Rankine scale, absolute zero, theoretical temperature, is compared to minus 459.67 degrees Fahrenheit. Looking up towards where it says H2O, water, freezes, on the Fahrenheit scale it's 32 degrees. On the Rankine scale it's 491.67 degrees. To convert from Fahrenheit to Rankine, Fahrenheit degrees is equal to Rankine minus 459.67, and to convert from Rankine to Fahrenheit, degrees Rankine is equal to the Fahrenheit degrees plus 459.67. Here's the chart for temperature conversion. Here's how it works. On the left side, you'll see KCFR. They are the temperature scales that you are measuring the temperature in. That's the number you already have. Let's say you have a temperature in Celsius and you want to convert it to Rankine. Start at the C. Go along the C row until you get to the column entitled R for Rankine. The equation is degrees Rankine is equal to 9 divided by 5 times left bracket degrees Celsius plus 273.15 right bracket. Always keep in mind bed mass when you're doing these equations. Let me do a few sample equations for you. Let's say, for example, I wanted to convert 122 degrees Fahrenheit to Kelvin. Looking at the equation, Kelvin is equal to 5 divided by 9 times left bracket degrees Fahrenheit plus 459.67 right bracket. When I start off with, I just substitute the degrees Fahrenheit for the 122. Now, to maintain accuracy, it is best to multiply 5 times the sum of 122 plus 459.67. That comes out to 5 times 581.67. That is 2008.35. Now I divide it by 9, giving me an accurate calculation of 323.15 Kelvin. Let's do another sample equation. I'm going to convert minus 23 degrees Celsius to Fahrenheit. First of all, I take the equation from the chart, which is degrees Fahrenheit is equal to the degrees Celsius times 9 divided by 5 plus 32. Now, what I've done, like I did before, is substitute the variable degrees C with the minus 23 degrees. First thing I do is multiply minus 23 times 9. And then I divide it by 5. That minus 23 times 9 comes out to minus 207. I divide that by 5. That gives me minus 41.4 plus 32 degrees. When I do perform that operation, you've got to remember I'm taking a minus number and adding a plus number to it. It comes out to minus 9.4 degrees Fahrenheit. Let's examine methods of heat transfer. Heat transfer is the movement of thermal energy from one place to another. When objects are at the same temperature, they are in thermal equilibrium. Thermal equilibrium is the state where objects are at the same temperature and there is no heat transfer between them. Always keep in mind that heat transfer is always from hot to cold. First method we'll discuss is conduction. Conduction is heat transfer that occurs in a solid. When molecules in the material are heated and the heat is passed from molecule to molecule through the material. Keep in mind that heat travels from hot to cold, or as it says here in this illustration, warm to cold. The vibration of the molecules is that electron action. The electrons become excited, they move, the molecules actually vibrate because of the movement of the electrons. This is actually the heat energy. Next one we'll look at is convection. In natural convection, convection is heat transferred by movement of fluid from one place to another caused by a pressure difference. When an object or substance is heated, a pressure difference is created. When you heat a liquid or you heat a gas, it actually expands, and when it expands, it actually becomes lighter. The amount of mass or weight per any given volume now becomes less, and in the case of the pot here, we see is this lighter material wants to float. It flows up to the top, and the colder material at the top flows down to the bottom. What you have, as illustrated in the pot, are circulating currents, and the mixing of these molecules in the circulating currents is a transfer of heat. Another type of convection is forced convection. Forced convection is heat transfer to a fluid when movement of the fluid is caused by some mechanical action. What we see here in the illustration below, we have cold air coming in from the right. It is moved by a fan. It goes through a heat exchanger which carries water, similar to a radiator or similar to the heater or the baseboard heaters in our lab. The heat is transferred from that coil or from the heat exchanger to the air and is moved out by the motion of the air through the fan. The last method discussed here is radiation. Radiation is heat transfer by electromagnetic waves emitted by a higher temperature object and then absorbed by a lower temperature object. As you can see in the illustration, the sun, which obviously is a higher temperature object, electromagnetic waves pass through the vacuum of space, not from molecule to molecule, and then they're imparted on the colder surface of the Earth. It warms up the Earth by these electromagnetic waves traveling through space. Here are a few examples of radiation. When a metal is heated and glowing red, a person that is standing a distance away from that metal, right, can actually feel that radiant energy. As an example, when you really heat up something really warm, even if you come beside a car that has been standing out in the sun, you pull it into the garage, you stand near it, and you will actually feel the heat coming from that. It's not the air necessarily that's being heated up, it's actually radiating energy. When one warms himself by a fireplace, the heat can be felt even through the air. Temperature between the fire and the person doesn't change very much, but the person can actually feel that radiant energy coming from the fire.